we move immediately to the fifth session. And in this session, we have 5 presentations. The session is entitled Solar Cells, Materials and Energy. And the chair of this session is Dr. Samy Shaat. He is with us. Dr. Samy, I hope you are here among the chairs. Yes, you are here, okay. And please, the floor is yours, Dr. Samy.
Assalamu alaikum wa rahmatullahi wa barakatuh.
You can share your camera if you want, Dr. Samy.
Yes. 1 minute. Okay.
Good morning.
Good morning. يعني أنا بس في البداية بدي أحكي أنا جاي خصوصا على نسائب الكهرباء فاصلة عندي والنت فجاي يعني مستضيفيني جزاهم الله خير.
الله يعطيك
يعني
العافية والله.
بسم الله الرحمن الرحيم. في البداية أود أن أشكر القائمين والمنظمين لهذا المؤتمر الرائع من حيث المشاركة والأبحاث والداعمون، حيث يتميز هذا يعني المؤتمر بالتعاون بين العديد من المؤسسات، وزارة التربية والتعليم العالي والبحث العلمي، وزارة التربية والتعليم، والأكاديمية الفلسطينية للعلوم والتكنولوجيا، ومجلس الإبداع والتميز، وكلية فلسطين التقنية في دير البلح وجامعة القدس، وأيضا يجمع بين قطبي الوطن والذي يؤسس لمرحلة جديدة للعمل المشترك إن شاء الله. وخص طبعا بالشكر للزميل والأخ الدكتور عز الدين عدوان. طبعا الجميع يعلم أن مشكلة الطاقة عالمية، ويسعى الباحثون لحل هذه المشكلة بشتى الطرق، ونتمنى أن يكون يعني في تعاون أكثر في هذا المجال. First of all, I would like to thank the organizer for this wonderful conference, especially for my brother, Dr. Izzeddin Adwan. Science brings us together. All of us know that the energy issue is global, so researchers are interested to find the best solutions for the issue. Today we will, just 1 minute. Today we have this session for solar cells, materials and energy. We have 5 manuscripts or papers. First one will be optical simulations of graded indexed material for solar cells model structure, TE mode case. The authors, Professors Muhammad Shaat and Yusuf Adwan. I don't have a biography for them, but I'm
Okay, I will start playing the presentation now.
بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. Hi everyone. Our study is
I think he has rises and
optics material or solar cell structure and transparent electric care.
Just 1 minute, please.
Yes. Okay.
Mr. Yusuf Adwan, he is a master student in Islamic University in physics department. I think he is very good and student. So let's listen for him. And thank you. Start. You can start now.
Okay.
بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. Hi everyone. Our study is optical simulation of graded index material or solar cell structure in transparent electric case. Now I will talk about the introduction and the purpose of the study, the electromagnetic waves, solar cell and the anti-reflection coating, the graded reflective index. And I will talk in details about the graded index model structure and the simulation and results and the conclusion. Solar energy is one of the promising energy which will draw all forms of energies combined in the future because their advantages which are renewable and alternative to oil and fossil fuels, environmental friendship. Now, the proposal. To understand why the interesting in this field, why the researcher interested in this field, and to understand the amount of the energy of the sun, the total power of the sun reaching to Earth is 5,416,000 electric joule per year. Whereas the global consumption in the years 2005 to 2010 was about 500 electric joule, whereas 0.01% of annual solar cell reaching Earth can satisfy the energy need of the whole world. Whereas the main purpose of this study is to increase the efficiency of the solar cell by increasing the transmittance and decreasing the reflectance from the solar cell surface. Electromagnetic waves. We know that the solar radiation reaches us as electromagnetic waves with the speed of light. The electromagnetic wave consists of electric field perpendicular to magnetic field, and both of them perpendicular to the wave propagation. So, the interaction between the electromagnetic wave with the anti-reflection coating will produce and will happen in two polarization, electric transverse polarization and electric magnetic polarization, as we will see in the analysis and simulation. Solar cell. Solar cell is the device which converts the incident light to the electricity by photovoltaic effect. The figure below shows the basic structure of the solar cell. The electron hole pairs, which formed by incident photons that satisfy the energy condition, where the photon energy must be larger than the gap energy. The electron hole pairs separate to p type and n type respectively to form an electric field on the depletion region, which offer the wanted voltage that allow the electric current flow. Anti-reflection coating. The main purpose of the anti-reflection coating is trapping the incident light to maximize the photocurrent of the solar cell by minimize the reflection. Anti-reflection coating exists on the upper surface of the cell to reduce the reflection of the incident light, where more layer in anti-reflection coating mean lower reflectance, as shown in the figure below. For zero layer, the reflection will be near 14%. Then for one layer will decrease to half, to about 20%, and so on. The reflectance will decrease as the anti-reflection coating layer increase. So, triple anti-reflection coating means that 3 layers are surrounded between the glass and the substrate material, as we will see in the model structure. The graded refractive index. The graded layer divided to sub-layers, and each sub-layer has own volume fraction, so that the refractive index will be close to the refractive index of the upper medium and the next medium. Then the effective index of refraction falls between the higher and lower index, as shown in the figure below. Now, to study the graded index layer, we have 3 profiles that described by the equation of refractive index, linear profile, a cubic profile, quantic profile, whereas the x in these equations describe the relative thickness of anti-reflection coating and its range falls between 0 to 1. Our proposed structure of anti-reflection coating consists of the graded index and zinc sulfide and titanium dioxide. These three material layer sandwiched between a glass layer from the upper and the substrate from the lower. The graded index has active refractive index, which will be from the upper layer or lies from the upper layer and the lower layer. Now, simulation and numerical results. As we know, the interaction between the light and the upper surface of the solar cell will produce reflectance and transmittance, where the reflectance and transmittance in transverse electric polarization case have been solved numerically by using the transfer matrix method and the software program Maple 18. The reflectance and transmittance in this model structure depend on a lot of parameters such as the incident angle and the relative thickness for the graded index layer and the dimension of the layers, which are D1 and D3, D2 and D3. Simulation and results. The variation of the reflectance and transmittance in the transverse electric polarization. If we change the incident angle for values of 0, 30, and 50 by using linear profile equation at x equals 0.3 for graded index layer, with fixing the other parameters as D1 equal 19 nanometer and D2 equal 50 nanometer and D3 equal 40 nanometer. In the result, we will see the reflectance, the minimum reflectance satisfied at incident angle equal 0, shown by solid red line. So the minimum reflectance satisfied for long range of wavelength. Also, for the same angle 0, the transmittance will show the maximum transmittance for long range of wavelength. Now, by changing the second parameter, which is the relative thickness of values 0.3, 0.5, and 0.8 for the graded index layer, with fixing the other parameters of the incident angle and the thicknesses of the layers, we will see the minimum reflectance and the maximum transmittance satisfied at x equal 0.3. So at x equal 0.3 and for long range of wavelength, satisfy the minimum reflectance and maximum transmittance. Now, by changing the thickness of values 14, 19, and 115 nanometer for the graded index layer at the normal incident with fixing the other parameters, we will see the variation in the reflectance and transmittance, but the best and optimal results satisfied at D equal 19 nanometer, which shown by dash blue line in both figures, in the reflection on the left and the transmittance on the right. for long range of wavelength. So, conclusion. The incident angle 0 is considered the best angle, which satisfies the optimal results of the transmittance and reflectance. So, the increase in the incident angle will decrease the transmittance and increase the reflectance. The refractive index for the linear profile equation at x equals 0.3 for the active layer is 1.734, which has achieved low reflectance 10 to 0 for long range of wavelength. The best thickness of the active layer is 90 nanometer, which expresses the minimum reflectance and maximum transmittance. High transmission and low reflectance have been obtained. Solar cell based on the graded index materials show promising future and can successfully be used to design high efficient solar cell. Thank you for listening.
Okay. Mr. Yusuf with us? Or Professor Shabab? Dr. Aiz?
Yes, I'm with you.
No, I mean that Mr. Yusuf with us or Professor Shabab?
I searched for him here in the list.
Okay.
Please, if you are in the session, raise your hand.
No, I mean that if any audience or any participant want to ask any question or comments. So I have two questions, but okay. Let's move to the other one. The other paper or presentation today titled Anti-Reflection Enhancement of Solar Cell Structure based on multi-type of nanoparticles for the authors Sahar Abu Abeid, Dr. Hana Musa, and Professor Muhammad Shabab. Ms. Sahar Abu Abeid, she got her master from Al-Azhar University, and Dr. Hana Musa, she is associate professor at Al-Azhar University also, and Professor Muhammad Shabbat is distinguished professor at Islamic University. So now we will start her presentation. I'm not sure if she with us or not.
Before I share, let me check if she's here. Just a minute.
Okay, check please.
I think I saw her. Yes, she raised her hand.
You can,
okay.
Fine. Good.
Right? Is that she, Sahar Muhammad?
Not sure. Yeah. I think so. Yes.
Sahar Muhammad, can you talk?
Yeah.
يعطيكم العافية ويسعد مساكم جميعا.
Sahar, you are welcome.
Yes.
But you can start now.
No, we will play her presentation, right? You prefer to...
Okay.
I play it from here. Maybe I have better internet connection.
Anti-reflection enhancement of solar cell structure based on multi-type of nanoparticles. Solar cell or photovoltaic is a promising technology that converts the sunlight directly into electricity through the photovoltaic effect. The aims of new research is to improve the efficiency of solar cell and reduce the cost of solar cell. Anti-reflection coating and nanostructure are methods used to improve the efficiency of solar cell. Anti-reflection coating deposed on the front surface of the solar cell to get the highest efficiency of solar cell by increasing the optical path length, then increasing the transmission. The strong interaction of metal nanostructure with light allows control over the propagation of light at nanoscale. That allows to design ultra-thin solar cell where the light is trapped in the active layer and efficiently absorbed. Model and theory. The structure of purpose solar cell consists of triple layer anti-reflection coating has impedance between cover from glass and substrate from silicon. The first layer of anti-reflection coating is an active layer which consists of 3 types of metal nanoparticles, and the second layer is zinc sulfide, and the third layer is titanium dioxide. The refractive index of the effective media of multi-types of particles based on the volume fraction of each material determined by effective media theory. The effective medium theory is valid only when the particle size is very much smaller than the wavelength of incident light. By using the combination of a Drude and Lorentz model, we determine the dielectric function of each material as a function of frequency. The reflection, transmission, and absorption coefficient for triple layer anti-reflection coating for both TE and TM polarization are derived by transfer matrix method. This figure shows the structure of anti-reflection coating, which sandwiched between cover from glass and substrate from silicon, and shows the light propagation in a triple layer anti-reflection coating structure. By applying the boundary condition at the interface, since the tangential component of electric field and magnetic field are continuous at interface, then the reflection and transmission amplitude expresses as we see. Then we can determine the transmittance and reflectance coefficient. reflectance and transmittance of TE polarization varies the wavelength at different incident angle. As we see in figures, as the incident angle increases, the reflectance increases. At incident angle 0, Maple program has been used to solve equations and plot the curves which describe the behavior of reflectance and transmittance with incident wavelength at different incident angles and different thicknesses of active layer. Reflectance and transmittance of TE polarization versus the wavelength at different incident angle. As we see in figure, as the incident angle increases, the reflectance increases. At incident angle 0, the reflectance decays to about 0 and transmittance attend to about 0.95. That means that at normal incident, the reflectance is minimum and the transmittance is maximum. The transmittance and reflectance plotted varies the wavelength at normal incident for different thicknesses of active layer. Maximum transmittance and minimum reflectance achieved at thickness 19 nanometer. Reflectance and transmittance of TM polarization with the wavelength at different incident angle. The maximum transmittance and minimum reflectance achieved at incident angle 13, as we see in figures. Reflectance and transmittance of TM polarization with wavelength at different thicknesses of active layer. At incident angle 13, the maximum transmittance and minimum reflectance achieved at thickness 19 nanometer. Conclusion. We have presented a design of a triple layer anti-reflection coating of solar cell by using transfer matrix method. We have observed that maximum transmittance and minimum reflectance achieved at normal incident of light for TE polarization and at 34 TM polarization. At minimum incidence, at normal incidence, the reflectance and the transmittance of both TE and TM polarization are completely identical. This means that there is no deviation between them. We believe that the triple layer anti-reflection coating is a very efficient technique to enhance the performance of solar cell. Thank you.
Thank you for Ms. Sahar.
Thanks for your attention.
Any questions or comments from the audience?
Maybe regarding the first presentation, Professor Shaat from Beit Hanoun, and he says Beit Hanoun is out of connection because of the last of the last night raining, and it was disconnected. But maybe we can call him by mobile phone if you like, if it's necessary.
Let's do it for the next paper, but now I would like to ask Sahar, did you compare your work or your result with the other work of the technique?
Can you repeat your question, please?
Did you compare your results or your work with other solar cell techniques?
We do this mathematical method, just mathematical. We not compare it with other.
Okay, but just. Okay, Sahar. Thank you so much for you. Any questions or comments from the audience? Thank you. Let's move to the third manuscript or presentation, which is titled by periodic silicon nitride metamaterial structure for enhanced solar cell efficiency. For the authors Horia Hamouche from Algeria and Professor Mohammed Shaat from Islamic University of Gaza. Dr. Ais?
Yes, please mute your mic, Dr. Samy, now. Mute your mic, I will.
بسم الله الرحمن الرحيم. الحمد لله رب العالمين، والصلاة والسلام على رسول الله ومن تبع هداه إلى يوم الدين. السلام عليكم ورحمة الله وبركاته. Good morning or good evening, everybody. First of all, I would like to thank Dr. Azzeddin Adwan and the committee of this conference. We are going to talk about periodic silicon nitride metamaterial structure for enhanced solar cell efficiency. This work was done by Dr. Horia Hamouche from Algeria. The outline of this presentation as follows: introduction, structure and methodology, optical characterization, conclusion. Performance of photovoltaic solar cells is affected by the optical energy losses. A great deal of these losses is caused by the reflection at the air glass front interface. Reflection losses at the air glass front interface account for 40% of the incident light, as you can see from this. To overcome this drawback, to overcome these losses, several anti-reflection coating materials on solar glass have been introduced as mechanism for light trapping. So, anti-reflection coating is one method used for light trapping for solar cells. Multi-layer dielectric planar anti-reflection coatings have been used to get more of the incident light in the solar cell. Silicon SINX is the efficient anti-reflection coating material due to its electronic characterizations. The thickness of the anti-reflection coating material is another important parameter that must be taken into account. In this work, we study the possibility of using n-binary unit cell silicon nitride metamaterials anti-reflective structure to minimize the reflection at the air class interface. So we used a new approach to minimize reflection. In other words, to increase transmission through this structures. In our structures, we are using alternating silicon nitride and metamaterial layers are placed on a glass substrate layer. Metamaterials is artificial materials. It has both epsilon and mu are negative. So we used this alternating silicon nitride and metamaterials in periodic, repeating these structures. As you can see here, metamaterials, silicon nitride, in the periodic layers, we use silicon nitride again for this unit. The thickness of the unit cell formed by these two layers is taken much smaller than the wavelength of the incident light. This conditions is imposed in our. The layer structure are treated in the framework of the effective medium theory. We used effective medium theory for two layers to be together. Effective medium theory is the right approach when the period is small compared to the wavelength. Method is used when the period is small compared to the wavelength to the light wavelength. Effective medium theory permits to simplify a layer structure to a single slab of homogeneous materials. Then this method allows us to simplify a layer structure to a single slab of homogeneous materials. The effective permittivity tensor and the effective permittivity tensor mu effective are expressed as you can see. The diagonal components are given by these equations, taking into account the relative permittivity and derivative permittivity and thickness of each layer of the unit. The transfer matrix method is used to derive the reflectivity and the air slab interface. In this study, we focus on reflections. Transmission can be obtained from the reflections through conversation energy law. Complete transfer matrix M for the slab between air infant layer and the glass infant substrate layer is obtained by multiplying the individual transfer matrices. This is conventional method and approach, and you can easily follow this approach. This we continue for deriving that reflectivity through transfer matrix. The reflection amplitude can be written in terms of transfer matrix coefficient, as you can see, and we can reflectivity can R is the square of the reflection amplitude. Here we have some result. We can see a decrease of reflectivity with increase of the number of periods. Here we have taken the number of periods 3, 5, 7 and the wavelength interval from 400 to 1200 nanometer. You can see here for n equals 3, 5, and 7. We found decrease of reflectivity when we increase the number of periods. Here, binary unit cell with layers thickness of 2 nanometer for the metamaterial layer and 6 nanometer for silicon nitride layer. Just we take unit cell, the thickness of metamaterial just 2 nanometer and 6 nanometer for silicon nitride layer. Here, if we increase the thickness of silicon nitride to be 8 nanometer, we found a decrease of reflectivity would increase the number of periods and the wavelength interval 600 to 1000 to 100 nanometer. You can see here in this region from 6 to 1200 nanometer. We found decreasing the minimum reflectivity. Here, we also increase the thickness of silicon nitride to be 10 nanometer. We found increase of reflectivity with increased number of periods and wavelength interval from 350 to 900 nanometer. In this region, the low wavelength. The 7 binary unit cell structure with layers thickness of 2 nanometer for the metamaterial layer and 6 nanometer for the silicon nitride layer seems to open the best possibility for minimizing the reflectivity at normal incidence. The reflectivity of the structure and the transfer magnetic polarized light for several incidence angle is decreasing with increase of incident angle. Here we have some results. We plot the reflectivity versus the operating light wavelength. We found a different decreasing whenever is observed for the angle theta equals 60 degrees. The percentage of reflectivity remains below 2.5% and the lowest reflectivity is obtained for the angle theta equals 45 degrees. Here we compared with the 1 unit silicon nitride intercoating layers on glass. We found a large percentage of reflectivity reaching approximately 38%. In binary unit cell silicon nitride metamaterial structure on a class can be used as an efficient mean for reduction reflection losses at the air glass front interface. Reflection losses can be minimized by optimizing the structure parameters such as the number of periods and the thickness of the unit cell layers. Compared with the reflective similar silicon nitride coating structure, the proposed structures are the suitable structures. Thank you for attention. All the best. Assalamu alaikum.
Okay. Thank you for Professor Shaat. Any questions?
We apologize for the quality. This is
yes.
Seems Professor Shaat was a little bit ill. We wish him a good health. Okay. Okay, so if there are no questions, we move to the next presentation.
Okay. Yes. The fourth one is titled Optimizing Solar Thermal Collectors Angles to Enhance Useful Energy Gain. For the authors, Dr. Muhammad Najjar from Palestine Technical College, Deir al-Balah, and for Professor Hala Al-Khuzandar from Islamic University of Gaza, and for Ms. Rawan Abu Mutlig, and Mr. Ahmed Harb, and Mr. Amir Ali Awad from Al-Azhar University of Gaza. I think here the presenter will be Dr. Hala, so I have 1 minute. Hala Al-Khuzandar is a full professor at Electric Engineering and Smart System Department. She is a winner of several national and international prizes, including Al-Najah University Best Published Paper in 2018 in the Scientific Journal. It was Medal Lecture 2015 and Cisco Prize in Science and Technology 2014. She is affiliated to several professional bodies. She is establishing member to the Palestinian Communication and Informatics Society. She has several publications in national and international journals with high reputations. Her research contributes.
Professor Hala is with us, right?
Yes.
If you like, we have the presentation recorded. We can play it, and if you like to present, both goes. But I will maybe run it. It's better for you, right?
Yes, run the video, please.
And if you would like to also to run your camera, it's also you can.
Okay. Assalamu alaikum.
Alaikum salam. Nice background. Where is it from?
It's the Islamic University. It's the girls' side. Yes, yes. It's where most of the time the students, the female students stay. Most of the time. It's a view from my window, from my office, but I'm not in my office now.
I understand, right. Okay, so it's ready. Let us play it. It seems Dr. Sam has internet connection problems. So.
Yeah, he mentioned that at the beginning, that he might have some problems with electricity and okay. Internet.
Okay, I play it now.
Assalamu alaikum wa rahmatullahi wa barakatuh. Today's talk title is Optimizing Solar Thermal Collector Angles to Enhance Useful Energy Gain. Speaker is Professor Hala Al-Khuzandar from Electrical Engineering and Smart Systems Department, Faculty of Engineering at Islamic University of Gaza. My co-authors are Dr. Muhammad Najjar, Dr. Azzuddin Adwan, Ms. Rawan Abu Mutlig, Mr. Ahmed Harb, and Mr. Amir Abu Awad. Gaza is laying on the Mediterranean Sea and in the hot zone where it has almost 300 sunny days per year, which makes it an attractive zone for using solar energy for useful energy, like electrical energy and thermal energy. it has an average of radiation of about 6 kilowatt-hour per meter تربيع at a tilt angle of 31 degrees, which makes Gaza is an attractive region for using solar energy. Why solar energy? Solar energy is one of the most attractive, clean, promising potential sources of renewable energy. According to the Palestinian Households Energy Survey, which has been held in July 2013, about 2/3, which is around 62% of population from Palestinian households, use solar heater for water heating, which is about 600 gigawatt-hour, more than $100 million annually. The optimum tilt angle of solar collectors differ at different regions according to the location of the geographical place due to longitude and altitude and latitude. All related studies to our study is focused on areas such as Surabaya, Indonesia, Cairo in Egypt, Toronto in Canada, Malaysia, Basra in Iraq, Tabaz in Iran, Medina in Saudi Arabia, and India. Although Gaza Strip has used flat plate solar water heating for a long time, the studies that focused on finding the optimum tilt angle is not available. Accordingly, the current study aims to find the best value of the tilt angle for the solar systems used in Gaza, Palestine. It is also noticed that in previous studies, most researchers found the optimum tilt angle for the solar collector based on the amount of solar radiation that reaches the collector surface. In this study, we aim to find the optimal tilt angle which provides the maximum useful energy gained by the collector. In this study, we used two programs to obtain the tilt angle and the incidence angle. These are Genesis software, which is one of the most useful programs in solar applications. In addition to Design Expert tool, which with response surface methodology, RSM, to get optimum tilt angle and in return obtain maximum useful energy gained by the collector. In addition, this study focused on effect of incidence angle with tilt angle on useful energy gained by collector. The optimum angle is determined for the 4 seasons of the year. This diagram shows the diffusion radiation and the global radiation. In Gaza region, along the year, we can see that the global radiation reached to around 240 kilowatt-hour per meter تربيع around June and July, which is summer season. The methodology, we start with the place of the study. Gaza Strip is the focus of this study, is in Palestine, is part of Palestine, and is located along the eastern shore of the Mediterranean Sea at 31.5 north latitude and 34.47 degree east longitude. The climate database was constructed based on Metronorm software for the period from 1991 to 2010. The average sun radiation reaches Gaza could be over 200 kilowatt-hour per meter تربيع per month in May, June, July, and August. Tilt angle and incidence angle of solar thermal collector. In the diagram below, we can see that the amount of solar radiation that falls on the solar collector surfaces throughout the year differed according to different factors, including the position of the sun in the sky, the surface orientation, as in the figure. In the figure, we will focus on 2 parameters, which is the tilt angle, beta, which is between the surface of the collector and the horizontal. And the other one, which is theta, which is the angle between the sun ray and the dormer surface. We can tell from this diagram, wherever the sun is changing, this will affect the incidence angle and also will affect the value of beta, which will result in the most useful energy gained. Useful gained energy using a flat plate collector. In the solar system, the solar thermal collector heat exchanger is the core of the system, which converts solar energy into internal energy of the conveyance layer. In this study, a flat plate collector with total surface area of 5 meters square was used. It can be mathematically found using famous Hotel-Wheeler equation. In our study, we used analysis using programs like TNSys, and in the TNSys model, the solar water heating system in the present study was designed and modeled using TNSys, which is one of the most reliable software for solar energy applications. The system consisted of 3 components: a flat plate collector, a storage tank, and a pump. Statistical analysis using design expert software. In the present study, statistical analysis using design of expert software is performed by response surface methodology, which is widely used for optimization operating variables. In this study, RSM was employed to evaluate the relationship between responses of useful energy gain and operating variables like incidence and tilt angles. The optimum tilt angle was obtained mathematically and statistically using the Design Expert 11 software program. The 2 significant independent variables considered are the incidence angle A and the tilt angle B, as presented in Table 1, where A corresponds to theta, which is the incidence angle, and B corresponds to beta, which is the tilt angle. And we have 3 levels, which is low, medium, and high. Low is symbolized by -1, middle is symbolized by 0, and +1 is symbolized the high level. And if we look to the table, we can see that level of value -1, which is the low, corresponds to incidence angle 0, tilt angle 20, middle 0 corresponds to 30 and 35, 1 corresponds to 60 and 50. This is the output of the analysis, and this is show all the months of the year corresponding to different combination of theta and beta. And we use January to represent winter, April to represent spring, July to represent summer, October to represent autumn. The following diagrams we will see next slides show the 3-dimensional surface plots of useful energy as a function of incidence angle A and tilt angle B. The curvature of 30D surfaces indicates that the tilt angle and incidence angle have significant effect on useful energy gained by the collector. This diagram shows the useful energy per kilowatt hour, incidence angle, and tilt angle. We can see that for a small incidence angle, we can get the highest useful energy, and corresponding the high values of tilt angles between almost 32 and 50, we can get the most useful energy. In this diagram, the tilt angle is between 32 and 50, and incidence angle between 0 and 50. And if we go far away from these values, the useful gained energy is declining, it's going to smaller values. The highest energy reached to 223 kilowatt hour in case of incidence angle less than 15. This diagram corresponds to spring, April. We see that also the most useful energy occurs at a small incidence angle, but also at the small tilt angles. So tilt angles goes from 0 to 32, incidence angles less than 15, where we can get the maximum useful energy. The maximum gained in this month was 484.6 kilowatt hour at tilt angle 26.72 degree and incidence angle of 10.97 degree. The summer season, which is July, we can see that also for a small incidence angle, which is less than 20, we can get also the highest useful energy. Also for small tilt angles, which is less, around 20 or less than 26, we can get also the maximum useful energies. The highest value, which is around 596.56 kilowatt hour, occurs at that angle, which is 20 degree and incidence angle of a 12 degree. If we go further from these values, the useful energy declines. This season is the fall season, which is October. In this season, we can see also for small angles below 12 or below 10 even, we can get the most useful energy. And also for small tilt angles, we can get the most useful energies, which is the highest value reached in October is 386.51 at a tilt angle of about 32 and incidence angle of 12. This is summarized, this table summarized the results we got from the figures. In January, the tilt angle 39.57 degree, incidence angle of 10.92 degree, get a maximum of useful energy 223.52 kilowatt hour. In April, the tilt angle is 26.72 degree, incidence angle 10.97 degree, with our most useful energy at 484.61. July at angle of tilt angle 20.15 degree, incidence 11.89 degree, we get 596.56 kilowatt hour. In October, 32.2 degree and incidence angle 12, we get useful energy 386.51. This diagram also shows the explanation of the table in a different way. Here is the angle in degree, here is the months, and here is the useful energy. The green line shows the incidence angle, which is almost stable all the months, around 10 to 12 degree. The blue line shows the tilt angle, which is vary actually according to the season. So it changes as we change months and the season through the year. And the red, which is also show the useful energy in kilowatt hour. So we can see that in January, the tilt angle is big and the gain energy is the minimum. As we go further into April, the tilt angle decrease and the useful energy increase, and useful energy reach its maximum, and the tilt angle reach its minimum value in July, which represents the summer. And again, the useful energy goes down in fall and the tilt angle increases. So in conclusion, we found that useful energy gained by the solar thermal collector used in Gaza was obtained by simulation through the year for different tilt angles and incident angles. The research study covered the 4 seasons: winter, spring, summer, and fall. The researchers used January, April, July, and October in particular to represent the 4 seasons respectively. Response surface methodology, RSM, is employed for optimization of tilt angle of solar thermal collector to maximize useful energy gained by the collector. It was clear from the result that the optimum tilt angle varies for different months or different seasons of the year, while incidence angle is almost stable around fixed value through the seasons. Its value must be small, ranges from 10 to 12 degree to get maximum useful energy, as again shown in the table. That incidence angles vary from 10.92 to 12 degree to get the most useful energy. The tilt angle, which is really varies from one season to another, which has the highest value in winter and the smallest in summer, and the highest gained energy is in summer and the smallest in winter. Further work is underway to complement experiments to verify all of the results at the optimum tilt angle to maximize useful energy. Thank you for listening.
Hello.
Thank you, Professor Hala. Is Dr. Shaat with us? Yes, he's here.
Yes, I came back.
Welcome back.
Yes, yes. Good morning, my sister, Professor Hala. How are you?
Now,
Fine, thank you. Thank you very much.
She moved from space to Earth. Yeah, she was now in space and now she's on Earth.
Yeah.
Thank you very much for presenting me, Professor Dr. Samy. And I hope that you liked my presentation, and thank you for listening to the presentation.
Okay. Any questions?
If you have questions, I'm ready to answer. Okay. There must be also Dr. Hussam al-Najjar. Dr. Muhammad al-Najjar, he must be somewhere around. I don't know if he's around.
I'm not sure. But any questions for Professor Hala? Just I have one question. How did you collect the data? Is it simulation, or you have a flat panel solar cell and get or collect your data?
It's a flat. It's not experimental. The experimental part will be next step. It's a flat collector, thermal collector, and the data have been collected from the source of the data. I think Dr. Izzuddin and Muhammad al-Najjar knows the source of the data.
Yes. So,
but it's not experimental. For sure, it's not experimental. The experimental part will come next. This is the answer for your question.
Okay, okay, that's good. There is a new techniques or system. I suggest you can add to your simulation data thermal, which is thermal generators. And there are also other techniques from these panels, which is a parabolic collector. So
yes.
Maybe, I think you can improve or you can enhance your work in the future.
It's just one step of a series of work. So it's just the beginning of the series of different work. So you might see that in the next publications.
But thank you very much for your interest presentation and work, and for all the authors. Maybe this is the first time to work with the BVT in Gaza, I think so. So thank you so much.
Thank you.
Any questions, Dr. Iz, from the?
Let's check if there are questions from the audience.
Or
we have here two questions. One from Engineer Raad Murad. We can allow him to ask also. He asked, why didn't you take the average of 3 months of each season instead of taking 1 month to represent each season?
Well, I think it's a very good idea to use like 3 months for a season, but usually people do this. So we just followed what other scientists do, that they present each season by 1 month. I don't know if that will make a difference. We can check that. Thank you for a question.
He is here. Maybe if you want to ask.
Yes, I saw him.
So, are there more questions?
Okay, can I comment my questions, please? I think taking the average of 3 months could give more exact results than taking 1 month to represent each season.
Yeah, I agree with you. Most of the people use 1 month to represent the season.
You can think of that as future work.
Yes. We can do that for 3 months and compare what makes the difference if we use the 3 months for presenting a season or using 1 month.
Yes.
But this is a custom use that people use 1 month representing each season. But we can try. It's a very good idea.
Okay. Thanks. It is. You have done a good job.
Thank you.
Okay. So now I think, where is Dr. Samy? Again, maybe connection problem.
I don't see him, yes.
Yes, again, he was disconnected. So our next presenter, we should move to the last presentation in this session. We have theoretical study of propagation of ballistic electrons through multi-layered structure. The presenter is Sarah Al-Khrabi. I hope she is here in the attendees. If she is here, we can maybe promote her to be panelist. Miss Sarah, are you online with us? Sarah Al-Khrabi.
Hello.
Dr. Samy. Yes. I thought you were disconnected, yes. And so I immediately activated the plan B.
No problem, no problem. Go ahead. You can complete your...
No, it's your chair. It's your chair. Okay. I'm searching for Sarah Al-Khrabi. I hope she's here. I cannot see her. Okay. Maybe you can introduce her if you
okay. The last presentation for Ms. Sarah Al-Khrabi and Professor Shaat and Dr. Mu'in Abeid. Sarah from Islamic University, and she is a MC student at Islamic University in Physics Department. Professor Muhammad Shaat is a distinguished professor at Islamic University, and Dr. Mu'in Abeid is assistant professor at Islamic University of Gaza, Physics Department. I think Ms. Sarah have a master's degree. Not a master's student, she got her master's degree. The presentation titled is a theoretical study of propagation of ballistic electrons through multi-layer structures.
Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everybody. Today I will present my work entitled as a theoretical study of a propagation of ballistic electrons through multi-layered structure. I am Sarah Al-Khrabi, Master Physics from Islamic University, Gaza. Participant in this paper, Sarah Al-Khrabi, Prof. Muhammad Shaat, and Dr. Mu'in Abeid. First, abstract. In this present paper, theoretical and numerical discussion of propagation of metamaterial ballistic electrons through 5 regions contains a triple potential barrier are presented. Also, the transmission probability of the mesoscopic structure with an artificial negative mass and energy less than the potential barrier are derived by using the matrix method to solving Schrödinger equation. So, the main aim is to show the possibility of a propagation of metamaterial ballistic electrons in 5 regions. Introduction. First, what is the mesoscopic devices? Mesoscopic scale or mesoscopic physics is the scale which are intermediate between microscopic and macroscopic scale. So recently, research efforts are directed toward the mesoscopic structure, which allow fabrication of artificial and novel electronic devices. This motivation concept is based on the current and future application in various technologies in electrons scale in electrons, such as electron optics, photonic band crystals, electronic devices, and so on. However, at very small length scale, electron transport ballistically. Look at this figure, and in A is show the diffusive transport when it occurs at macroscopic scale, and the electrons have encountered number of random scattering when it travel from one point to another. In contrast, in B, the electron move ballistically, which means there is no interaction between electrons, and this happen in the small scale range in meso and nano scale. The propagation of ballistic electrons through a triple barrier. A triple quantum barrier has been studied since the 1990s. So nowadays, many electronic applications are based on electron transfer through a single and double and triple potential quantum barrier. In our present structure here, all barriers have potential V1 and V3 and V5 respectively, and have an artificial negative mass M1, M3, M5. In addition to the well have V2 equal V4 equal 0, and have M2 and M4 for effective mass. In this paper, we using the algebraic solution by using the matrices according to the variation of effective mass and potential energy through this structure. The Schrödinger equation describes the motion of electron get as in these equations. Numerical computation. In the analysis 1, a metamaterial ballistic electron traveling through our structure, where the quantum barriers B1, B2, B3 are in figure 1, have a potential V1, V3, V5 respectively, where V1 equal V5 equal V3 equal 0.56 electron volt, which have an artificial effective mass M1 equal M3 equal M5 equal minus 0.023 M0, and the quantum wells with V2 equal V4 equal 0, M2 equal M4 equal 0.4 M0. 2. The figure gives the profile of transmission coefficient as a function of energy for different thicknesses of D1. The thicknesses of the well as 10, 15, 20 nanometer. 3. When thicknesses D2 are considered equal and kept constant at 10, 15 nanometer, and behavior of transmission varies of energy when the thicknesses D2 equal 10, 15, 20 nanometer and D1 equal 10, 15 nanometer. So, in the results, figure 1, the transmission T probability varies of energy for triple quantum barrier double well at constant D2 equal 10 nanometer and varying D1. Here, V1 equal V3 equal V5 equal 0.56 electron volt and V2 equal V4 equal 0 electron volt, and M1 equal M3 equal M5 equal minus 0.023 M0, and M2 equal M4 equal 0.4 M0. In figure 2, also the transmission T probability varies of energy for triple quantum barrier double well at constant D2 equal 15 nanometer and varying D1. V1 equal V3 equal V5 equal 0.56 electron volt, and the potential will equal 0, and the mass M1 equal M3 equal M5 equal minus 0.023 M2, and the mass of well equals 0.4 M0. In the figure 3, the transmission also probability varies of energy at constant D1 equal 10 nanometer and varying D2. Last, in the figure 4, the transmission T probability varies of energy at constant D1 equal 15 nanometer and varying D2. Finally, discussion. The figures 1 and 2 show the case when the thicknesses D1 varies at 10 nanometer, 15 nanometer, 20 nanometer, and thicknesses D2 kept constant, first at 10 nanometer and second at the 15 nanometer respectively. The figures 3 and 4 show the case when the thicknesses D2 varies at 10, 15, 20 nanometer and the thicknesses D1 kept constant, as in figure 3 and at 10 nanometer and in figure 4 at 15 nanometer. It is critical to note that the transmission coefficient gives a unity. When the energy less than the potential and increased of D1 shifted the peak to left 0 to 0. On the other hand, when D2 is increased, the peaks are in the same point. Conclusion. In conclusion, by numerical simulations, we extended the studies about the analogy concept between optical and quantum metamaterial to show the propagation is possible through a metamaterial's ballistic electrons. And experimentally, the design is difficult to find realistic data for mesoscopic structures and classical data. The approach is good enough to future work, which could be implemented by an adjustable or tuning method. Theoretically, the analogy between waveguide structure and quantum mesoscopic structure has been verified. Reference. And finally, thank you for your attention. Thank you. Bye-bye.
Okay, thank you, Ms. Sarah.